Okay. Hello, in this session, let's practice concavity. Let's continue the topic of concavity and inflection points. This is exercise number 2. Find the points of inflection of the function x to the power of 5/3. We actually see the graph, we even see the point of inflection, but let's explicitly get the point. What we need, the potential points of inflection are the points where the second derivative is 0, second derivative is 0, or where the second derivative is undefined. Okay, let's check. First of all, domain for this function, this is like third root of x to the power of 5. Third root, cube root are taking all of the numbers. Yeah, we don't have to be worried about excluding, for instance, negative, like for the even roots. Okay, let's find the derivative. Derivative is 5/3 x to the power of 2/3. It's, it has to be 0. Let's check. Let's rewrite a little bit. 5/3, and this is cube root of x squared. It means this expression, this is the first derivative. Let's wait. I mean, this was correct. This was correct. No. Let's do it maybe on the side. The first derivative is 5/3 x to the power of 2/3. Okay, I probably did so many first derivative tests. Probably the same like you. Okay, I will keep differentiating. Let's differentiate one more time. 5/3 times 2/3 and x to the power of -1/3. Okay, let's rewrite a little bit. This will be 10/9, and x to the -1/3 is a cube root of x in the denominator. Okay, that means now let's see. Second derivative is defined like this, and it has to be 0. Fraction is 0 if the numerator is 0. Numerator doesn't depend on x. In this case, because I'm supposed to write something like this, but that's not true. We have no solution from that part. No x values. Now, second derivative is undefined if this expression is undefined. Fraction is undefined if we will try to divide by 0, if the denominator is 0. Denominator is 0 if x is 0. And 0 belongs to the domain. 0 is a potential candidate for the inflection point. But let's check the sign of the second derivative. Where is that second derivative? This is a good formula. Okay, 0 is the only point. I can substitute negative number, -1 for instance, then we will get negative number. When I substitute +1, 10/9 cube root of +1, positive. It means second derivative is definitely changing the sign at 0, from negative to positive. Function is concave down and then concave up. At 0, at x equals to 0 is an inflection point. And we may see this is the inflection point. Function is concave down and then concave up. We have the graph. We don't have to draw, but I just include the graph to see better. Okay, but please always consider both of the cases and not right away assume that this is the inflection point, because second derivative may not change the sign at that point. Okay, exercise number 3. How many points of inflection does the graph of the function f have if the second derivative is provided and it's equal to x squared times x plus 1 cube times x plus 2 to the power of -4. Okay, We may see right away the candidates. I can rewrite a little bit x squared, x plus 1 cube, and x plus 2 to the power of 4. So we can see second derivative is 0 if the numerator is 0. Numerator is 0 if x is 0 or x is negative 1. Second derivative is undefined if denominator is 0. Denominator is 0 if x is negative 2. Yeah, a little bit quicker algebra. And now we're not assuming we have 1, 2, 3. I don't know. Yeah, 1, 2, 3. Definitely not 4. Maybe 3, maybe 2, maybe 1. But we have to figure out the sign of the second derivative. Okay, let's place them. Negative 1 is negative 2. Let's make it nice. Negative 2, negative 1, and 0. We will test the sign of the second derivative, and this is good for. Okay, when I place negative 3, this x squared, actually, it's always positive because it's squared. X plus 2, the quantity x plus 2 to the power of 4 is also always positive. That's these, actually, they don't really affect the sign. Yeah? But x plus 1 cube affects the sign. When, let's see, when the quantity is positive, cube positive. When it's negative, cube negative. Negative 3 plus 1 is negative 2 cube. It will be negative number. These are positive. Okay, let's take negative 3 halves. Negative 3 halves plus 1 actually is still negative. Cube negative. Function is not, a second derivative is not changing the sign. Okay, let's take where we are. Let's take negative half. Negative half plus 1 is positive half, cube positive. And let's take 1 plus 1, 2, 2 cube positive. Okay, so second derivative is negative. Function is concave down, concave down, concave up, concave up. Only at negative 1. This will be the inflection point at negative 1. Only at negative 1, second derivative is changing the sign. Only one inflection point. Yes, we can see we have to always check. And if we remember a little bit from the first derivative test, the same happens. We may notice algebraically why this happens. X, and from that x we got 0. The x squared is 0 if x is 0, and that 0 came from the multiplicity of 2. We have the even power. Yeah, that means if the quantity is taken to the power of even power, we've got that 0. This expression, in this case is a second derivative, will not change the sign. Either positive or either negative on both sides. Depends on the rest of the formula. And also negative 2 came from that factor, and that factor is taken to the power of even number. The same thing. Either negative or positive, depends on the function, but will not change the sign. Yeah? That's always the hint, the indicator, which we may answer this question right away, not even doing the whole work. I can see x squared, that's 0, will not change the sign. X plus 2 to the power of 4 will not change the sign at negative 2. But x plus 1 cube, it will change the sign because it's odd exponent. At negative 1, we will change the sign. Okay, just a little bit of hint. Okay, next one. Exercise number 4. No? We have a function f having a following property. F prime of x equals to 0 at 2. F double prime, the second derivative is less than 0 for all of the x's less than 2, and the second derivative is greater than 0 for all of the x's greater than 2. Which of the following could be the graph of f? Let's maybe label this A, B, C, D, and E. Okay, that's what we know. if the first derivative is 0 at 2, we will have a horizontal tangent. Horizontal tangent. Because slope of the tangent is derivative and slope of the horizontal lines are 0. Horizontal tangent. We don't know if it's like local maximum, minimum. We don't know, but we know that it's horizontal tangent. And let's check. Horizontal tangent at 2. Oh, horizontal tangent at 2 looks like horizontal tangent at 2. Horizontal tangent at 2. Horizontal tangent at 2. Nothing to be eliminated. Okay. Second derivative negative. Function is concave. Yes. Function is concave down. And second derivative is positive. Function is concave up. Concave down. No, concave up. For all of the x's less than 2 and greater than 2 respectively. Okay, let's check the concavity. So definitely this is not good because function is concave up on the entire domain. Not good. Function is concave down on the entire domain. Not good. This one, D, I'm looking at D. Okay, concave, concave down, concave down, concave down. That means I like this one. Concave down, and then inflection point probably, and concave up. Yeah, I think this one, but let's eliminate. This is concave up for all of the x's less than 2. That's not good. And this one, yeah, we have to have concave down for this is 2. And we can see at some point, probably 1 is the inflection point. Function is concave down. This is okay, but it's actually also concave up. Yeah, on that interval is concave up, which is less for all of for some of the x's less than 2. That's not, yes, that's not good. It means E is the correct answer. Okay, now let's look at my exercise number 5. Oh, let's see what we have. Wow. At exactly 2 of the labeled points in the figure, the derivative f prime is 0. Okay, we can probably figure out B and A because horizontal tangent. Okay, so derivative f prime is 0, f prime is 0. Yeah? At exactly 2, that we have no other zeros. Okay, no other zeros. Now the second derivative 0, this is supposed to be 0, comma. The second derivative f double prime is not 0 at any of the label points. And that's probably they are not inflection points. On the table below, give the signs of f prime, f double prime at each marked point. Okay, let's look at A. Point A definitely have horizontal, function have horizontal tangent at A, then first derivative is 0. We actually know that. Now, let's assume that dot, actually it's below the x-axis. Is below the x-axis, then function itself is negative. Yes, function is negative. This is negative. And function looks like it's concave up. If it's concave up at A, second derivative is positive. Nice. Let's do B. You may pause the video and you can try to analyze on your own without me, and then you can put back on. Okay, B has horizontal tangent, derivative is 0. B is above the x-axis, like with respect to the blue curve, is above the x-axis, the value of the function is positive. However, is concave down. If it's concave down, the second derivative is negative. And then let's investigate C. C, if we will draw tangent line, it's the slope will be negative. That means derivative is the slope of the tangent is negative. Derivative is negative at C. I don't know why I'm starting with the first derivative. Okay, point C is above the x-axis, then the value is positive, and it looks like it's concave down. Yeah, it's still the part of concave down. Then it will be negative. And then D. D is below the x-axis, that means its value is negative. Slope of the tangent, which is derivative, is big, positive. And function looks like concave up. Concave up, second derivative positive. Okay, nice analysis of the signs of function, first and second derivative. Exercise number 6. Let's see. A function f has the value at 520. Value of the first derivative at 5, 2. Value, actually second derivative, I think this is double prime. Double prime, second derivative is negative for all of the values greater than or equal to 5. Okay, couple of conditions. Which of the following are possible value for f of 7 and which are impossible? 26, 24, 22. Okay, so what we will do, we have a couple of information. I can try to draw the situation. We have value 5, and I know the scale is 0.20. Now, yeah, that means I did this one. F prime at 5 is 2. This means that the slope of the tangent line at 5 is 2. I can say that this slope is 2. Then if this is 2, let's get a couple of values on the tangent line. Yeah, that means this is tangent line. Remember, tangent linear approximation. Value, if we will move one unit to the right, the slope is 2, this will be 22. And 7, because that's what we are looking for. This will be 24, but this is still not, yeah, this is approximation, 22, 20, I mean 24, 22 is. Now, this condition, second derivative, is negative. Then we know that function is, and you may answer, function is concave down. If the function is concave down, I can draw, yeah, definitely will be placed below the tangent. Yeah, we remember function is concave down for all of the x's equal to or less. I mean, I supposed to start from, shall I erase this? Okay, I supposed to start at 5. I don't want to because we have only this information. Okay, that means now we can nicely see the value at 7 cannot be 24 because this will be the approximation if we will use the tangent line, but the actual value is somewhere here. That means definitely not, could be, looks like 22. I didn't really plan it to do this way, but it's not option for 24. 24 is the approximation and not 26, of course. It's, yeah, impossible for 24. I mean, for 26 is impossible. 24 could be really close to 24, but it's definitely lower than 24. Yeah? This will be the option, the possible option listed here. Okay, I hope we understand this. This is, I draw concave down because second derivative is negative. Okay, that's we getting this concavity. Okay, my next question. The table below shows y as a function of x, so that y is equal f of x. According to the data in the table, is the derivative of f of x negative or positive? Is the second derivative negative, positive, or 0? Okay, so we, what we know? We know that the first derivative, let's start with the first derivative, okay, first derivative. First, if the maybe start with the function because we have the value. We know, for instance, this first function is increasing, yeah, then its derivative is positive. If the function is decreasing, yeah, then its derivative, it's negative. First derivative is, let's see. Increasing means that as we increase the x values, I mean, when we go, yes, when we increase the x values and we actually increasing 5 and even have the exact the same intervals, we jumping by 5 units, 5, 10, 15, 20, 25, 30. Let's see what is happening with the values. Are they getting higher? 10, 16, 25, 35, 50, 75, yeah, 105, 150. Yes, that means function is definitely increasing, then the sign of the first derivative is positive. This is the answer for the first derivative. First derivative is positive. Okay, now what about the second derivative? How we can recognize? We know that if function is concave up, then first derivative is positive. If function is concave down, first derivative is negative. But how can we get from the values? How can we get this condition? Just really quickly, let's look at, I can draw it. I don't know, yeah, how exactly the function is because we will not plot, we can still plot the points. But let me just draw it because I know that function is increasing. That means I draw this increasing and this. But let's, yeah, this is concave up, that's concave down. Yeah. Let's analyze. We did talk a little bit, but let's see what's happened when we moved along the x-axis with even number of units. Let's make it more clear. Let's see how the values are changing. So we can see this will be one value, yeah. Then this will be another value, and another one, yeah, and another one, because what I'm trying to see, how the difference, yeah, we can see this is one, like a one, and the difference in values. Then this is another difference, yeah, because the size of the increase, we just going up again, we going along the x-axis, the same number of units by 1, by 2, by 5, doesn't matter. If we going, yeah, let's look at this blue, the blue, like the increase in size. Then this one is bigger, this one is even bigger. The other one, the corresponding value for 25 will be somewhere here, even bigger. Right? That means if the size of increase of the y values is getting larger, then function is always concave up. Yeah, I was just, this is longer, and this is longer, and this is longer. Because let's actually analyze, let's look at this concave down. Yeah? This will be one value. Now we're moving the same units, and actually I just want to stress this out a little bit better. Yeah, that's concave down, because that's always the case. It's not maybe easy to show. That means this is one increase, that interval, that jump. Now we may notice that arrow is the jump, the size of increase is actually smaller, and then again this one will be even smaller. That means the increase is increased because both of them are increasing, but the size of the increase is getting smaller for concave down. That means, please, yeah, also note that that's the characteristic of concave up and concave down based on the values. I mean, if the size again of the size of increase of the y values are getting bigger, then function is concave up. And if it's concave up, the second derivative will be positive. Of course, this one will be negative. And let's look at the size, because we have the values. And I can even, well, I can write even this, but let's just check. This is increased by 6 units. This one, how many units we have between 16 and 25? 9. And 25 and 30, 35, 10, 35 and 50, 15, and then 25, and then 30 and 45. That means these jumps, these increase, I mean the size of increasing is getting larger as x gets larger. Okay, so this is definitely the answer. Function is concave up. I didn't include the y values, but that's how we can recognize if the size of increase in the y values are getting bigger as we move by the same number of x, the same units along the x-axis for each value. Okay? But if the values are getting smaller, the increase, the increase, that the small distances between the corresponding values are getting smaller, then function is concave down. Okay. It's helpful, it's worth to note. Okay, another one. Let's skip this one, it's almost solved. Let's do applications. Let's struggle a little bit. Okay, so in what we have? Scenario. An infection flu spreads slowly at the beginning of an epidemic. The infection process accelerates until the majority of susceptible individuals are infected, at which point the process slows down. Okay, you can read probably again in your head. If R of t is the number of individuals infected at the time t, where R is concave up and where R is concave down. Okay. So we can see it's definitely increasing. Yes, we assuming, and actually it's assuming that it's increasing, but we don't know if this will be time and this is R of time, the number of individuals. So what we know, near the beginning of the epidemic, the graph of R supposed to be, because it's spreading slowly, I don't know if I like this, at the beginning of the infection process accelerates, okay, but it's spreading, but it accelerates until the majority of susceptible individuals are infected. Okay, at which point the process slows down. Okay, that means I will say the numbers, and then it's slowing down and it's concave down. Yeah, I hope this makes sense, because the infection accelerates. That means as we move the same number of days, the cases are growing each value. Yeah, the increase in size is bigger. That means function must be concave up. Yeah, the increase in the y value is actually getting bigger, getting larger as we move the same number of days. For instance, I don't know if it's days, the units days, and then at which point at some point process slow down, and then it's still increasing, slowing down, but this will be, of course, the inflection point. I mean, that's just the graph. So that we can say that the epidemic began to subside, which the number of new cases is decreasing. Yeah, we still have at the inflection point. Yeah, this will be the inflection point. T, let's say T sub 1. This will be the inflection. And it's still, yet it's still increasing. We can see the values are still increasing, but the cases, the number of cases are decreasing. I mean, no. The number of cases are increasing, but the day by day, it's smaller value, because the differences between the values are getting smaller. Concave down, that's what we just talked for the previous. Okay, that means we can just leave it. This will be the inflection point, wherever the process slows down, and at the beginning is faster, like increase in number of infected people, and then it's still increasing but slowing down in this size. Okay, less people. Okay, and I have this question. I have two more. Okay, let's look at this. Similar situation like the spreading the flu. The vase in figure below is filled with water at the constant rate, constant volume per unit time. Graph y equals to f of t, the depth of the water against time t. Show on the graph the points at which the concavity changes. Okay, that's we have, yes, the water is coming inside the vase. Okay. And if it's coming in with the constant rate, we may see, yes, we may see that the vase is getting wider up to that point. Then we will need more time. Yeah, even if we put the same amount of water, the height. Yes, the height, that's what we have to do, the depth of the water. The height will increase, but it will increase slower. Concave down. And that's me. Let's do it. That point, this point, and this point. Okay, it means it will increase, but concavity-wise, it will be concave down. The difference in height will decrease. Yes, these differences will be smaller and smaller. In general, the height, the water increasing, but the size of the increase is getting smaller. Yeah, the rate of change of the second derivative, of course. Okay. Now, what's happened? And this looks like the widest point. Yeah, that's the widest point here. Now, the same rate of the constant rate of water coming in, but now the vase is getting slimmer. Then the height will still increase, but will increase faster up to that point. Y sub 2, Y sub 1, Y sub 3. Yeah, that's the height. That's the height. Okay, that means up to that point will increase concave up, because the size of the increase is getting bigger, faster. We will not even realize how fast we actually reach that point. And it's still not the widest point. It is still concave up, because it's getting even slimmer. I mean, I can make the concavity even more steeper. That means that, oh no, I don't want to bend it too much. I just have to indicate that it's even steeper. Okay, and then this is the slimmest point. And from now on, again, the increase in height will be slower, because the vase is getting wider. Then I have to draw concave. Oh, this one, concave down. Okay, concave down, up, even more up, and down. Okay, we have the graph. We did this one, but now what they also asking us, at what depth is function f of t growing most quickly, most slowly, and then estimate the ratio between the growth rates at those two depths. Okay, That means, of course, the function f of t grows most quickly wherever the vase is the skinniest. And that means this will be the most quickly at, let's say, I can answer this, at the point y3, yeah? Wherever is the skinniest. Most slowly, wherever is widest. I wanted to say fattest, but that's not appropriate. Wherever is the widest at y sub 1, okay? And estimate the ratio between the growth rates at these two depths. What we can do, we can try to figure out maybe the diameter or the radius. Let's say diameter, yeah, because we have to like, if we will think about like a disk, the water of disk with the really small height, yeah, we have like a disk. Yeah, it's kind of like, it's like a circle, pi r squared the area, pi r squared, and we have to fill out that water of disk. And I can say that maybe that small, the skinniest diameter is 4 times, kind of like 4 times, just for the equal, 4 times smaller than this one. Yeah, and the same will be for the radius. I mean, when we will take this one is the 1 and this one, let's say 3, this will correspond to, or maybe let's say the skinniest and the widest. And then when I will take the ratio, because they would like to find the ratio, one area divided by the other one, the skinniest and the widest. And if that ratio of that area, because we have to fill out with the water that area, it's less than 1, then of course that, I mean, that will be the ratio, whichever is slowest, whichever. We know that the big circle is slowest. Okay, that means I can maybe say that if this radius is 1, this one is 4, yeah, because it's 4 times bigger. Or we can say 5 times bigger. Let's say 4. I mean, this will be 1 pi over 16 pi. We can simplify 1 over 16. I mean, this ratio is showing us that the bigger circle to fill out with the water, the bigger disk, it's 16 times slower. That's the ratio. If the number will be 16, it will be 16 times faster, but it's 1 over 16, 1 per 16. We will fill out one small circle, like of water, this one disk, and at the same time, we have to wait 16, yeah, 16 times slower. Okay. I think, yeah, we did the analysis, and I have one more and I will finish the session. Okay, this one will be probably quick because we have similar situation, but it's not a vase, it's just the sphere, and we know where is the fastest, when is the slowest rate, where the size of the increase is getting larger, when the size of the increase is getting smaller. Okay, water is pumped into the sphere at the constant rate as seen in the figure. Let h be the level of the water at the time t. Yeah, the same thing, like the vase. Which graph corresponds to the process? Let's say A, B, C, D, E, and F. Okay, it's mean at the beginning, if the rate of the water is like the same, we can see it's getting wider and wider. As we have to wait, it's increasing, but the size of the increase is getting slow. It's getting smaller. Yeah, because the same amount of water, but we need to put like more area and more area. That's we will for the same amount of time, the height will increase slower. So definitely function is concave up. Down. That looks like this one is concave down, this one is concave down, but I don't. This one looks. Why I can't write? No. Oh, okay. This one is concave down, and then at the widest point, the height will increase faster. Concave up. Yeah, definitely not this one. Definitely not this one. This one is no, because it will not, it has to be symmetric, like the concavity, because it's the sphere. It's the same. It will be respectively like speed up with the same rate as it was slowing down. Yeah, for the height. That means this is not good. This is not good. This will be the good graph. Yeah. Always when it's like the size of increase is getting faster, like starting from here and up, then function is concave up. At the bottom, if it's getting wider and wider, the size of the increase is getting smaller, then function is concave down. Okay, thank you. You may try to solve these problems one more time, as always. Okay, enjoy your practice, enjoy your concavity. Thank you.